Hello, concrete friends. I'm Tyler Lay, and today we're going to talk about different types of pores inside concrete. In the last video, I talked about the importance of pores. I talked about some things that we could do to try to minimize the pores inside of our concrete, but no matter what we do, we're never going to get rid of all of them. We're just not. So we should just learn about them, right? Learn what they are, what they're all about. This plot shows size down on the x-axis, and it shows a range of different sizes of pores that are inside concrete and compares them to other things that are also inside concrete. So let's start out with the smallest pores, something people call CSH interlayer space. Now these are the space in between the layers. These sizes are between 0.5 and 2.5 nanometers. Okay, they are too small to impact the strength or the permeability. Okay, or to, I guess, have a significant impact on the strength or permeability. And they're always there. They're what typically grows when the CSH comes together. They're just part of it. Okay, and they fall here. Next size. Capillary pores. Now these are a big deal. These are ones that we can control somewhat and we can pay attention to. These are anywhere between 2.5 nanometers to 5 microns in size. And this is space not taken up by the cement or hydration products. They're typically irregular in shape. They're not spherical. They're kind of maybe worm-like. They have all kinds of different shapes. Okay, they're long and they're in between the cement grains. And this volume is extremely dependent on the water to cement ratio. Remember, that's the spacing of the cement grains and the degree of hydration. And they are very important for creep, shrinkage, and permeability. And we're going to talk a lot about capillary pores. Okay, most of the time when people say pores, although all of these things are pores, most concrete people are talking about capillary pores. And again, these are the pores when I have cement grains that hydrate. Okay, these are the stuff, the wide open regions in between. This kind of wide open region, that's a capillary pore. And these small regions, small, really, really hard to maneuver regions in between here, okay, those are the CSH interlayer space. And you can see the capillary pores shown at the top here. And we're showing about the CSH particles, or the aggregation at least, are about in this size. The calcium hydroxide is about in this size. And then let's move on to our next two types of bubbles or voids. Entrained air. These are 10 microns to 1 millimeter in size. These are spherical voids that are stabilized by a specialized surfactant for frost durability. This is an air entraining admixture is added to concrete. Also, this 1 millimeter, is this some magical number? No, it's not. It is not. Okay? It's not. Someone just had to pick a point where to say, is there, when I use air entrainer inside concrete, the majority of my voids are less than 1 millimeter. But I've seen all kinds of concrete that have 0 air entrainer in them, and they still make voids that are spherical that are less than 1 millimeter in size. So don't think that this is just some magical definition, because it's not. It's just somebody did their best and picked one. And then there's entrapped air, and the magic number that people say is 1 millimeter and larger in size, and that's not some magical. These are just kind of the larger voids. These are kind of the smaller voids, okay? And this is the air that's trapped during mixing. These are the huge voids. These have big impact on durability, big impact on strength. They're a big deal. And we can go back up to our graph and we can look at them. There's our air entrained voids coming in there, and here's our entrapped voids coming in here. Again, it's just nice to have a graphical representation of all these different sizes of pores inside concrete. Differential shrinkage in a slab can cause it to lose contact with the subgrade. And this can lead to cracking. This can be a big deal. How does this happen? Well, If I during curing, when I put a tarp over it or some kind of curing method on top of it, I'm going to keep my concrete nice and moist inside. But as soon as I take that curing off, okay, the top of the concrete is going to start to dry. And the bottom of the concrete is going to still be wet because it's still in contact with the bottom. But the dry stuff is going to want to shrink. And the wet stuff won't. There's actually going to be a strain profile that's going to look a lot like this. And the top is going to want to shrink and the bottom won't. And it causes it to curl up. And this is called curling. This is what most people call curling. Some people call it warping as well. Let's not worry about that. It's a volume change. And if you have an edge loading on the surface of your slab or your pavement, you can cause cracking and you can cause it to fall down. And that's not good. People don't like that. That's one problem. But let's say if my shrinkage is restrained, so I've got a really, really, really strong base. It's holding it in place, okay? Holding that slab in place. And as that concrete starts to shrink, okay, it tries to shrink, it tries to get smaller, but it's being held by this base, that can cause these cracks to form, okay? This restraint is holding it back and cause these cracks to form. But there's something else we have to know about. In low water cement ratio mixtures, what's low? I'm going to say anything less than a 0.40, okay? And it happens above a 0.40, it just becomes much more prevalent below a 0.40. There's an additional type of shrinkage that can occur that can definitely lead to cracking if it's restrained, if it's held back, okay? And the hydration of the paste, what happens is it actually consumes water. The reaction absorbs and uses water, okay? And this causes the pores inside of the concrete to lose water. And this starts in the first few minutes of mixing. Really does. It starts really early on. And it keeps happening through several days because our reaction keeps happening through several days. And this is another reason why curing is so important for these materials. But when this shrinkage happens before set is cured, again, when the reaction happens, and this shrinkage is happening before set, but the concrete's still plastic, then we call it chemical shrinkage. But when it occurs after set, that might happen through the first couple days of the concrete's life. We call it autogenous shrinkage, okay? But they're really both tied to this reaction of the water being consumed during hydration. You might say, how are we ever going to deal with this? How are we going to do this? Well, you would cure. You really want to cure. Here's the problem, though. If I have a decent sized element, I can try to put water on the outside to fight that internal consumption of water, but I'm never going to make it inside. I'm not going to make it. So if you want to go to a lower water to cement ratio, then you need to come up with a new approach. And one really, really cool idea is this idea of including lightweight aggregate that have been saturated prior to mixing. And this is called internal curing. Internal curing. This idea that I'm going to take a saturated lightweight aggregate. So I've got an internal water reservoir inside my cement paste. So this is really helpful when my water cement ratio is low. Not as helpful when my water cement ratio is higher. Okay, at least not for autogenous shrinkage and chemical shrinkage. Anyway, I have this saturated lightweight aggregate. I have thirsty paste. Want to suck up that water. And the aggregate's actually able to give it to the paste around it. The water will lose from the inside of the aggregate and is given to the region around the outside. Pretty awesome, right? Some of the leaders, at least in the United States on this, Del Bence, Jason Weiss, people that are just doing really cool work, really awesome work on this. This means that you want lightweight aggregate particles that are small and well distributed. almost like air voids for freeze thaw, small and well distributed. You also want them with pores that are not too small and not too large. And we're just lucky that most lightweight aggregate has the pores that are just about the size that we want. And the short answer, there's plenty of really fascinating research done on this, but the short answer is that if you replace your normal sand with lightweight sand at about 20% replacement, then you're going to get a lot of benefits from this internal curing. And there's definitely individual tests you can do to figure out exactly what you need for your lightweight aggregate. But 20 to 30% is a good number to get started with. Thanks. Take care.